This is a UNIVAC 1219, a computer from 1965 that has just hosted a Minecraft server.
Wait, you're on camera. Did it work?
It worked!
I can't believe it!
But we'll get back to that one. About a year ago, I went to finally check out VCF East, also known as the Vintage Computer Festival East. For those unfamiliar, it's basically a big convention for retro computing nerds such as myself. There's room after room of various people's collections on display. I saw pen plotters, a shrine to Windows 95, absolutely awesome electromechanical teletype equipment, a manga user's guide to the Macintosh, and capacitors the size of soda cans. But tucked away in one of the buildings in the back, I came face to face with an absolute beast. See, VCF East takes place at the InfoAge Museum in New Jersey. About a century ago, it was a Marconi wireless station receiving radio transmissions from across the Atlantic. In the 50s and 60s, it housed a giant dish antenna for radar and satellite experiments. And nowadays, it's a museum with exhibits documenting various areas of technological development, including computers. And right in the center of that room is the UNIVAC 1219, a computer from the mid-60s about the size of 3 to 4 refrigerators side by side. And man, is this thing cool. It's got the front panel blinking lights, the big tape reels, and all the output gets printed on the world's loudest teletype. It was everything 60s sci-fi movies promised me computers would be. UNIVAC is short for Universal Automatic Computer, and in the middle of the 20th century it was the name in computing. Well, besides Big Blue. UNIVAC was the computer of choice for Wile E. Coyote, Isaac Asimov spoofed it when naming the computer Multivac in his stories, and it's the computer that made headlines when it successfully predicted the 1952 presidential election would be a landslide, even when his human operators didn't believe it. The UNIVAC company lineage goes all the way back to the ENIAC, the 1940s University of Pennsylvania research project considered to be the first computer. For a very precise definition of computer. ENIAC's job was to compute tables of artillery firing trajectories for the US Army, and about 20 years later, this UNIVAC, Model 1219, the military version of the 418, actually wasn't that far off. From the late 60s into the 80s, these machines could be found on Navy battleships, listening to radar and aiming guided missiles. Nowadays, though, this UNIVAC here seems pretty happy to live out its civilian life at the museum, playing the occasional game of Hunt the Wumpus and printing out ASCII art portraits of George Washington and Spock. At least, that's what I saw it doing during the live demo at VCF. Naturally, I got into a bit of a conversation with the guys operating the machine, and I asked if anyone was writing any new software for it. The answer I got was, not really, but there was a stack of about a dozen manuals and an emulator, if I was interested. And, well, I was interested. I got home, fired up the emulator, read the manuals, and got to work. Being designed in the early 60s, the UNIVAC here feels in some ways so close to a modern computer, and in other ways worlds apart. It has registers like any CPU, but those registers are 18 bits wide, instead of 16, 32, or 64. Everything's binary under the hood, of course, but it means any number you see written out in the documentation will be an octal, rather than hex, since 18 bits divides nicely into 6 octal digits. It's got all the math operations you'd want, even hardware multiply and divide, but that math is done in 1's complement instead of 2's complement, with all the fun negative zeros and weird wraparound carries that entails. Even some easy instructions are a bit hard to understand at first. Got any guesses for what selective set, selective clear, and selective complement do? As it turns out, those are pre-Woodstock ways to say bitwise OR and an XOR. One of my favorite quirks, though, is that this machine doesn't have a stack pointer. Now, sure, you've got the instructions necessary to call into a subroutine and return, but instead of pushing a return pointer onto the stack, the return jump instruction stores it in the memory address right before the start of the subroutine, and all functions end with an indirect jump to that return pointer. It's all a little weird, but as it turned out, with enough practice and a ton of trial and error, I managed to get a program of my own working. Because I'm a hack who's run out of ideas, the goal I chose this time was one I've covered before on this channel: pi computation. Last time, I did it using an implementation of the BBP summation, and a few tricks to extract decimal digits one at a time. Oh, and I also did it using electromechanical relays. Here, it's almost exactly the same, except this time I'm using the Bayard formulation instead of BBP. It's a bit more complicated, which is why I didn't use it in the relay machine, but in software it's almost no extra cost and it converges about 3 times faster. It took a weekend's worth of work, but I finally had the emulator spitting out digit after digit of pi. I want to make myself clear, I am really grateful for the work Dwayne, one of the volunteers at the museum, did writing up the emulator and assembler I used to program the UNIVAC here. Without it, I probably would have given up on this project by day one. That being said, the developer experience here had a few limitations. For one, this was a .NET app, which made running it on Linux not entirely trivial, and the assembler being a QBasic program meant I needed to install DOSBox to run it. This meant my typical testing workflow was save the file, mount it into DOSBox, run the QBasic emulator, copy the file out of DOSBox, restart the emulator, type in the file path for the tape, set the address to the bootloader, and hit run. That, plus the fact I didn't originally have the source code for the emulator, made debugging my programs a bit frustrating. So, in a spark of stuck-on-the-train productivity, I started writing my own emulator and assembler in Rust. At first, it was just a quick program to inspect memory images, but by the time we pulled into the station, I was running small UNIVAC programs and the 8-click testing tango had been reduced to one CLI command. This emulator was also fast. A table in one of the manuals lists the runtimes in microseconds for each instruction on the UNIVAC. I had my emulator count out the machine time against wall clock time, and I found it ran anywhere from 200 to 400 times faster than the real hardware. I wasn't even going out of my way to write hyper-optimized code. It's just a testament to the improvements in computer hardware over the last 60 years. And probably also the Rust compiler. Developing for the UNIVAC was now a lot simpler, but actually sitting down and writing out assembly programs was still a tricky and error-prone process. I would have been a lot more comfortable in a higher-level language like C, but at least as far as I can tell, there weren't any C compilers that targeted a UNIVAC 1219. I guess it probably doesn't help that the 1219 predates C by several years. This was about the time I showed off my work to my buddy Nathan. We both share an interest in programming for the TI-84, but while I was doing ray tracing and Minecraft programs, Nathan worked out an incredibly hacky way to get the functional programming language OCaml to run on a calculator, garbage collector and all. The trick there was to take the functional OCaml code and convert it into a dysfunctional language like C to leverage the existing compiler toolchains for the calculator. Neat stuff. So in a friendly bit of nerd sniping, I took a shot to see if his talent for plugging things that shouldn't be plugged together could turn on something for the UNIVAC. And boy, did he deliver. The idea Nathan had was that rather than trying to find a UNIVAC C compiler, or worse, trying to write our own, we could actually take advantage of a major compiler like GCC, so long as we used GCC for what it was good for. GCC doesn't have a UNIVAC backend, so getting it to generate code in UNIVAC instructions wasn't going to happen. But there were some other architectures of note, including RISC-V. RISC-V is just another instruction set architecture, like x86 or ARM or 68K. The only difference is that RISC-V is open sourced and offers some really minimal instruction sets. RV32i, the base integer instruction set, only has 38 instructions, but GCC will happily compile a working binary out of these instructions. Instead of getting GCC to accommodate all the little oddities of the UNIVAC instruction set, if we could get the UNIVAC to accommodate all the little oddities of RISC-V, we could get C code running on it. Nathan threw together a toolchain that compiled C to RV32i, and a bytecode interpreter on the UNIVAC that could emulate the RV32i architecture. And as if by magic, C programs just started working on the UNIVAC. Or, to be more precise, the UNIVAC emulator. We'd been messing around with this stuff for a few months at this point, and still had no idea if any of it would work on the real machine. So, after reaching back out to the people at InfoAge, who were pretty surprised to hear we had programs to run on their computer, we worked into time to head back over to the museum and give all our programs a test. One last thing you might be wondering, though. If we have access to a UNIVAC and have the programs to run on it, how do we get those programs onto the UNIVAC? It's not like we could just stick a flash drive in. Fortunately, that question was already answered for us when we got there. It all starts with the RAM in this machine, which, owing to it being built in the 60s, is core memory. Core memory is a really neat technology from a time when semiconductor memories simply cost too much per bit. Instead, the memory was formed by a mesh of wires with ferrite rings wrapped around them. Depending on which wires had currents flowing through them, and the nonlinearity of magnetic hysteresis, a particular ring would be magnetized, and that magnetization stored a single bit, which could be read back out through a current induced in another wire. One handy side effect of storing your bits magnetically is that even if the power gets shut off, all those bits will still be there, living in the RAM the next time you turn the computer on. And that's what happens here. Of the 40 kilowords of memory in this UNIVAC, 32 are set aside in a write-protected section as a bootloader. This loader is a tiny program that does just enough to turn on the paper tape reader and load in a second bootloader encoded as a bunch of holes on this ribbon here. The second bootloader is a fair bit smarter, and it can be used to load more in from the paper tape, perform a few system functions, and in our case, load from one of the I/O channels. Fitting with the whole giant computer thing, these I/O plugs are massive 90-pin chonkers that connect the CPU to the rest of the hardware units. And if we can control all the pins here, we can send data into the UNIVAC through one of these from something more modern. And that's exactly what the museum does. Thanks to Tattoine again, this little box contains an Arduino that bridges the gap from 90-pin parallel into RS-232 serial, which isn't too hard to turn into plain old USB. At the end of that chain of core memory, paper tape, giant cables, and microcontrollers, we can just plug our laptops in and load our program straight into the machine. Another fun detail is that there's no operating system on this computer at all to launch a program. Just a front panel and a bunch of lights to see the states of all the registers. When you load a program into memory, nothing happens until you manually point the program counter to the starting address and press start. And here on the other end of the machine is the output. This is the Pi program I handwrote in assembly, and it's working great. It's pretty fast too. In a matter of a few seconds, this computer can churn out more digits than my relay machine could do in the better part of an hour. And the UNIVAC here is limited by the speed of its teletype. Pi shows off the speed of assembly, but what about C code with the bytecode interpreter? Obviously, virtualizing a whole different processor on the UNIVAC isn't going to beat bare metal code. By Nathan's estimate, each RISC-V instruction takes on average around 40 UNIVAC instructions. But what the C programs lacked in speed, they make up for in number. We have a ton of them, since once we had a compiler, it became pretty easy to just try a bunch of different pieces of C code we could find online and see what would work. There were plenty of tiny demos like computing prime numbers, a database of the periodic table, even using AES to encrypt and decrypt a piece of text. Some of my favorites, though, are the more era-appropriate programs. Like Eliza! For those unfamiliar, Eliza was a famous early example of a chatbot from the mid-60s. You can talk to it through the terminal, and it'll type a response back to you. Part of the suspension of disbelief here comes from the program being presented as a simulated therapist, which explains why often Eliza responds just by rephrasing whatever the user says back into a question. Using certain keywords can also cause Eliza to use a scripted response. It's a neat trick. Even if compared to the language models of today, this program is incredibly simple. Impressively simple, I'd say. Even in the 1960s, computers were generating AI slop. Also from the 60s, how about the language BASIC? Famously included in just about every 80s home computer worth its salt. With this interpreter here, you can type in a program right on the UNIVAC and run it. No laptop, serial cable, or crazy bootstrapping process needed. Many a computer nerd got their start in this language, myself included, and it's just great to see it running on a computer that can match it in age. One of our goals with this project was to give the museum some more demo programs to show off to visitors on this machine. And to me at least, few things are cooler than being able to type a basic program or chat with Eliza on era-appropriate hardware. If it hasn't become apparent already, one of the best things about running stuff on the UNIVAC here is watching it get printed out on the teletype. Not only is it a gorgeous piece of electromechanical hardware in its own right, but it also adds something physical and real to the software we're running. Any program on this machine involves a bunch of bangy noise with each character getting printed out, and the products of each hard day's work are immortalized on a scroll of paper that can cross the entire room and makes a perfect souvenir. So it seemed natural that some of our programs took advantage of the printout we were making, like Figlet, that Linux command line program that generates an ASCII art banner of whatever you type in. We got it running here. Or my Pi program. After seeing it working for the first time, I felt it needed a few, white space changes to make the formatting really pop. Yeah, I'm pretty proud of this one. It's going in my collection for sure. That's not to say that working with a physical teleprinter is easy. Compared to a terminal emulator, the teletype is less forgiving. It still prints in ASCII, thankfully, but not all the characters are there, and some of the ones you're familiar with, like underscore or caret, are replaced by these weird little arrows. Unlike a software terminal, there's no line wrapping either, so if you've got a program that forgets to print a new line, the carriage will happily keep typing over the character in the last column again and again. We actually got inspired by this to try a technique called overstriking, where by typing multiple letters in the same space, you can get a wider range of brightness levels, and turn an image into a surprisingly sharp-looking ASCII art printout. Not bad for something that started as a bug. And that's not to say that our only bugs with the UNIVAC were in the printout. On our first visit to the museum, none of our programs worked. At least I'm pretty sure Pi doesn't have an H in it. The code Nathan and I wrote was only as good as the emulator we tested it in, and as it turned out, that emulator didn't perfectly match the real machine. It took us a fair bit of manual reading and running small test programs on the physical UNIVAC to determine exactly how the virtual one should work. And after we patched the emulator, we were able to patch our programs. All this debugging took place over the course of multiple visits, about once a month. But remember, this UNIVAC is from an era where machines were shared, and programmers would need to work things out on paper long before they got time to test on the real thing. If anything, our experience here feels pretty appropriate. In rare cases, the gremlins weren't even our fault as programmers. Occasionally, the UNIVAC itself wasn't in the mood, and the operators at the museum, Stephen and Bill, would need to fix it. Thankfully, the machine's manuals are full of schematic diagrams, and the cabinets open up pretty easily. This machine predates the widespread use of integrated circuits, so instead it's loaded with a bunch of little cards like this one, that can be unplugged and swapped out. Talk about repairability. There was one last idea for this UNIVAC that we wanted to try. As a reminder, we were loading in programs off our laptops through the machine's I/O channel converted into a serial connection. And where there's a serial connection, there can be an internet connection. Let me explain. PPP, or the point-to-point protocol, is a way to wrap up IP packets and send them down a serial line. The idea is that one computer, which doesn't have an internet connection, is hooked up to another computer that does. And the second computer shares its connection with the first one by forwarding whatever internet packets get sent down the line. In our case, the UNIVAC was connected to a Raspberry Pi. It took a ton of debugging, but eventually we were able to get the most basic of web servers running on the UNIVAC. This page here you're seeing in Chrome, that was hosted straight off the UNIVAC, right down to the marquee text. But we can do even better than that. What would you say to a Minecraft server running on a computer built before the moon landing? People said it was impossible. And when I say people, I mean me. But I'll let this video of Nathan logging in speak for itself. So yeah, it takes about 30 seconds to spawn into an empty void, and after that the server stops responding to packets and the client eventually times out. You might call this barely a server, and you'd be absolutely right, but I hope you'd agree something as anachronistic as a 1960s computer the size of a fridge conversing with a Minecraft client to the point where the client decides to log in is still at least a little cool. Just a tiny bit. So there we have it. The thumbnail clickbait paid off after all. And I even have one more special surprise. In the description, you'll find the code for the emulator, the C toolchain, and all the little programs shown off today. And even a version of the emulator that runs in the browser. It's not perfect, but it should mean that just about anyone watching can try their hands at UNIVAC programming. I'm excited to see what people come up with. Also, don't forget, if you're going to VCF East this year, to check out this machine in person. There should be a demo scheduled sometime during the weekend, and I'd highly recommend taking the chance to see this magnificent monster in action. I mean, look at what happened to me. I saw it a year ago, and now I've checked off one of my bucket list items. I want to thank everyone at the InfoAge Museum for graciously trusting us with their one-of-a-kind machine. Stephen and Bill, the operators at the museum, for helping us get this thing running. Nathan for his insane compiler work and getting the Minecraft server running. And of course, Dwayne, who, without all his prior work to make programming on the UNIVAC feasible, this project wouldn't have gotten off the ground. As for me, well, as much fun as I've had, I think I'm ready for something a bit lighter. After all, the saying goes, never trust a computer you can't lift.